All right. Before we jump into today's lecture, I want to point something out on the Moodle page real quick. All right, so I've updated some sections and put homework assignments in them. So like right now, if I am not mistaken, right here is homework 11. And if we clicked on that, it says that it is due today at 5. I never put a assignment submission form thingy up there for that. So what I'm going to do is I'm going to put one up with a due date of Friday at 5 for those people who may have missed that, so that they have time to do it, so that it's not going to penalize it. Okay. I'm going to do that literally right now while I'm thinking about it, so that I don't continue to do silly things like that. So let's see. Assignment. Come on. Okay. I think maybe this is why I forgot to do it. All right. So that would be homework 11 online portal. I want one file, PDF. What we do Friday, which is the 29th. No. Oh, you're being difficult. 17. All right, save and return to course. Underneath the instantaneous power, average power, and maximum average power transfer section, there is a homework assignment as well. That one I have set due for this upcoming Monday. So it's 4 problems to be done in the next, let's see, if today's Wednesday, Thursday, Friday, Saturday, Sunday, 5 days. So that seems reasonable enough. And then I have the next few homework assignments set up to be 2 days after that, and then 2 days after that, etc. So that I have all of the homeworks posted for the material that should be done before our exam, which is on next Wednesday, correct? I think that's what we agreed to because people had exams next Monday. All right, so we're gonna have the exam next Wednesday. So today, we are gonna be talking about complex power, and on Friday, then we will talk about power factor correction if we don't get to it today, which is a possibility. So Friday's lecture will be the last bit of material that is on the upcoming exam. Covering power factor correction really won't take more than 20 to 25 minutes, so we can use the remainder of that class period as a review session for the test, because on Monday, we're gonna start talking about filters. So everybody okay with that plan? So Friday's lecture material is the last stuff that will be on the exam next week. All right, okay, let's talk about complex power. This is entirely a review of stuff that you covered in Circuits 1, but it's also where a lot of people make a lot of mistakes, so we're going to kind of take our time and go through things here. All right. So as we have seen the last couple of days, dealing with instantaneous power values can get very, very cumbersome very quickly because of the sheer amount of information that has to be carried along, right? Not only do you have some magnitude, but you also have to worry about phase angles, frequencies, and all that jazz. To alleviate that, electrical engineers developed what is called the complex power representation that is based off of using effective values. So you may recall that when we had an instantaneous voltage, V of t is equal to Vm cosine omega t plus theta v, and an instantaneous current value of Im cosine omega t plus theta I, we found that the average power delivered to a generic load was 1/2 Vm Im cosine theta v minus theta I. We can split this up to be Vm divided by the square root of 2 multiplied by Im divided by the square root of 2 cosine theta v minus theta I. And this happens to give us V effective multiplied by I effective cosine theta v minus theta I, where V effective and I effective are Vm divided by square root of 2 strictly for sinusoidal signals. So this trick here only works for sinusoidal signals, although we could develop complex power relationships for triangular waves and all that jazz, but they're not nearly as useful. So we're going to restrict our discussion to steady state sinusoidal analysis because that's what we've been talking about. So these engineers noticed that this operation, V effective times I effective times the cosine of theta v minus theta I, is simply the real part of this complex multiplication. V times I complex conjugate, where I'm going to define V with that squiggle over it as an RMS phasor. So that will be our phasor voltage divided by the square root of 2, meaning that this guy is Vm square root of 2 angle theta v. And similarly, I as an RMS phasor will simply be a regular phasor current divided by the square root of 2, which is Im over root 2 angle theta I. So we're able to carry all of that information for our average power in by simply multiplying two quantities, okay, that are based on simple phasor relationships that we've dealt with before. So this complex power, V multiplied by I conjugate, has a lot of information buried within it. So I'm going to denote the complex power here. So let's say that S with a bar over it, because it is a complex number, is V times I complex conjugate. S is the symbolic representation of the complex power. And because it is the product of voltage and current, it inherently has dimensionally units of watts, right? But that would be extraordinarily confusing because it would be hard to differentiate that from instantaneous power, average power, etc. So electrical engineers developed a specialized unit to represent complex power, and that unit is the volt ampere. So dimensionally, exact same thing as a watt, but if we're ever talking about a quantity and we say that it's 780 volt amperes, we are specifically talking about complex power. We can represent this mathematical operation as a rectangular form or a polar form representation. So let's start with a polar form representation. So we would have S with an angle of theta S, where S without a bar over it is what's known as the apparent power. Apparent power has units of volt amperes as well, because it simply represents the magnitude of the complex power. So if you ever hear about a quantity in volt amperes that doesn't have an associated phase angle, that means that we're talking about apparent power. If there is an associated phase angle, then obviously we are talking about the complex power. This angle, theta S, is the exact same thing as theta V minus theta I. Simply the difference in the phase angles between the voltage and the current. And it is known as the power factor angle. Obviously, if it's got degrees, that means the dimensions are degrees. If it doesn't, it's in radians. It's an angle, so there's nothing fancy about that at all, okay? So in the polar form, our complex power tells us what the apparent power is and what our power factor angle is. In the rectangular form, actually, let's do a quick thing here real quick. So mathematically, S is going to be, since it's the magnitude of the complex power, if we take the magnitude of the phasor voltage times the RMS phasor voltage times the complex conjugate of the RMS phasor current, our apparent power is simply V effective multiplied by I effective. All right. So over here, I'm going to draw a picture. I'm going to say that I have some complex power that is not remotely a straight line. S, like so. All right. The length of this guy is our apparent power, and this angle is our power factor angle, where this is our real axis, and this is our imaginary axis. Now we can project this portion onto the real axis. And similarly, we can project the complex power onto the imaginary axis, which would allow us to express the complex power in a rectangular form, right? So that would be simply, well, it's the wrong color. S cosine theta S plus JS sine theta S. And if we substitute in our definition for our apparent power, this gives us V effective, I effective, cosine theta S plus J V effective, I effective, sine theta s. This whole quantity, V effective, I effective, cosine theta s, is the exact same thing as the average power that we discussed previously, literally 100%. So this guy represents average power. We typically denote it with the letter P. So I'm going to put a P over here on my graph. And the units of average power are watts. This guy over here, we're going to call Q. So the imaginary part of our complex power. And we call it our reactive power, which has of volt amperes reactive. Bless you. This picture that I've drawn is what's called a power triangle. And we can infer an awful lot of information from this power triangle, but before we do just that, I want to develop a relationship for one further quantity, okay? So these are all of our basic complex power relationships. Now let's take a look at one other item, okay? So we know that our average power P is equal to V effective times I effective times the cosine of theta s, which we could rewrite as S cosine theta s. From this, we can see that the cosine of theta s is simply the ratio between the average power and the apparent power. So this cosine theta s is really a measure of efficiency in this system, right? The average power represents what portion of the apparent power is capable of doing mechanical work, all right? We call this number, or this representation, the power factor, all right? Which is why theta s is called the power factor angle, okay? The power factor is a number that ranges from -1 to +1, okay? So a power factor of +1 means that the load is capable of absorbing all of the power that is delivered to it. A power factor of -1 means that the load is actually supplying all of the power that's delivered to it. And a power factor of 0 means that the load is absorbing none of the power that is delivered to it. So if we have an inductor, for instance, we know that theta s is going to be positive 90 degrees. Well, actually, we may not know that theta s is going to be positive 90 degrees, but we know that, I know that, but you may not know it yet. But we do know that theta v leads theta I by 90 degrees. So we can see that there is a 90-degree difference when we take theta v minus theta I. It will be 90 degrees. So that's why for pure inductive loads, our power factor is 0. For purely capacitive loads, our power factor is also 0 because we're taking the cosine of -90 degrees. And the reason why that happens is because if we determine the instantaneous power for a capacitor or for an inductor, the DC portion, the average power, is 0. So what that means is that in capacitors and inductors, every cycle that power is sent to that element, half of the time it is being absorbed, and the other half of the time it is being sent back to the source. So it's absorbing and sending back over and over and over. It's never actually doing any work whatsoever, just being transmitted, being sent back. This is the reason for the concept of power factor correction that we're going to talk about later. If our power factor is too low, it means we're running our system inefficiently, and it's costing the power company money because they have to generate it whether or not you're actually going to use it. If they didn't generate enough apparent power, brownouts and things like that would occur. But they have to, so they have to spend money to generate this power for it to just get sent back to them. So they're effectively burning coal or putting wear on their hydroelectric turbines or however they're generating their power for no real specific use, and so they'll penalize you for it. So power factor correction is a means by which to fix a couple of things. All right, so going back to our power triangle, I'll draw a new one here because we're kind of running out of room. Let's see. So here we have S, and the projection onto the real axis was P. The projection onto the imaginary axis was Q. Here we have theta S. So we can easily switch back and forth between the polar and rectangular representations of complex power, just using basic trigonometric identity, nothing remotely hard there, right? But this power factor angle, theta S, actually tells us a whole lot about our system. So for example, when 0 is less than theta S is less than positive 180 degrees, meaning that our angle is positive when we constrain it to be within plus or minus 180 degrees. Our power factor is considered lagging. This means specifically that the current through the element is lagging the voltage. Well, anytime that the current is lagging the voltage, this implies that our load is inductive in nature, okay? When the angle is specifically 90 degrees, our load is purely inductive, but at all other points when our angle is positive value, we have some resistance connected to some inductive quantity as well. Let me ask you guys a question. Does it matter if the resistance is connected in series to the inductance or if it's connected in parallel? Will we still get a positive phase angle? So let's take a look at what's happening. Right. So if we have a resistance in series with an inductance, the equivalent impedance, ZEQ, is R plus J omega L, right? Where L is a positive quantity and R can technically be positive or negative here, but we've only ever dealt with positive values of R. Our phase angle for this guy will always be positive, right? Because we have, because the imaginary portion is always above the horizontal axis, our phase angle will always be positive. If instead we had this guy, our equivalent impedance is going to be R times j omega L divided by R plus j omega L. It's a little bit harder to see what's going on here, right? So what I'm going to do is I'm going to multiply by the complex conjugate of my denominator, which will get rid of any imaginary parts in my denominator. So if I multiply this by R minus j omega L over R minus j omega L, what I get is, let's see, positive j times negative j is positive 1. So I'm going to have omega squared L squared R. So I'm multiplying this whole thing by j omega L. So j omega L times R times negative j omega L, yeah. Then I multiply j omega L times R times positive R. Divided by R squared plus omega squared L squared. So I have a rectangular number, and the sign on the imaginary portion is positive. So I should always have a positive phase angle, even if the two impedances are connected in parallel. So it does not matter whether they're in series or in parallel. Anytime I have a resistor connected to an inductor, I should observe a positive phase angle, okay? So for all cases, inductive loads have positive phase angles. If 0 degrees is greater than or equal to theta s, which is greater than or equal to negative 180 degrees, meaning that our angle would be considered negative if we restrict the angle to lying between positive 180 and negative 180. In this case, we consider our power factor to be leading. That does not look good. Which in turn implies that our current leads our voltage through our load, which is true for capacitive loads. And I shouldn't need to go through and tell you it's going to work for both series and parallel, because the math here tells us exactly why it's going to work out that way for our inductive example. So really the only other thing that I want to point out before we start getting into some numerical example problems would be that you can actually determine the power factor specifically, but no other quantity, without actually knowing voltages or currents across your load, right? And so the reason why we can do this is from the definition of the power factor angle, right? Theta s, our power factor angle, is by definition theta v minus theta I. Well, if we look at our definition for impedance, Z is equal to V over I, and it does not matter if I'm looking at this as a RMS phasor or a regular phasor. This is going to be Vm over Im with an angle of theta v minus theta I, which means that the angle of the impedance, theta z, is mathematically identical to our power factor angle, theta s. So if we ever want to know what our power factor is, we don't ever, and that's the only piece of information we're looking for, we don't ever actually need to calculate voltage or current or anything like that. If we know what the impedance is, we know what the power factor is. It's that straightforward. All right, so any questions regarding these fundamental relationships here? We got plenty of time to talk about stuff if you guys got a question. If not, happy to move on. All right, so nobody's saying much of anything. So let's take a peek at an example. Let's say that I have an RMS voltage source. So let's say it's going to be 400 angle 0 degrees volts RMS. And it is going to supply multiple loads. And let's do a third one over here. So we have 3 loads in parallel. Let's say that load 1 is an electric motor of some sort. And the motor nameplate tells us that it's going to draw 65 kVA at a power factor of 0.6 lagging. We have another load. Let's say that this one is maybe a bunch of fluorescent lights. And so it's going to draw 12 kilowatts at a power factor of 0.98 lagging. And let's say that for whatever reason, load number 3 is a railgun. So this is the loads being supplied by the power factory on a battleship or something like that. And so it's going to draw, let's say, 30 kilowatts at a power factor of 0.7 bleeding. Unfortunately, a railgun is pretty much the only load I can think of that will actually operate at a bleeding power factor. What we want to figure out is what the complex power being supplied by our source is. So S source. I want to know the current that's being drawn by the source. So let's call this I phasor. I'm going to define this on our diagram because knowing this will tell us what gauge of wire that we would have to use to safely supply power to all of these loads. And let's also determine the power factor at which the source operates. So how might we go about this process? Anybody have any ideas? And we're neglecting something fairly fundamental here, and we'll talk about how we can take that into account a little bit later, but we are neglecting the impedances of all of our wires that are connecting things here, which may not be a valid assumption depending on really the length of the wires. So on an actual naval battleship, you literally have miles and miles of electrical wires running through all the bulkheads and all that kind of good stuff. So they're going to have some real contribution to the power transfer in the system. But for our idealized model, we're kind of lumping that to our loads for now. Yeah. So how can we determine any of these quantities? Anybody have any thoughts on a basic fundamental level? So we know the voltage drop over all three of the loads, but we don't know the impedance of any of the loads. So finding the current is going to be arguably a little bit difficult, but let's go back to something real simple and fundamental, okay? So we are told that load 1 absorbs a particular amount of, is it apparent power, reactive power, or average power based on the units here. So a kVA is apparent power, right? Or volt amperes are for apparent power. So we have the magnitude of the complex power and we have the power factor. So that should be enough for us to get the complex power absorbed by load number 1. For load number 2, we have 12 kilowatts. 12 kilowatts represents average, reactive, or apparent power. Average power. And we're also told the power factor, so this should be enough information for us to calculate the complex power absorbed by load 2. And for load 3, we have a similar information to load number 2. So we can calculate the total complex power absorbed by these 3 loads. Now my question to you guys is the sum of the complex power absorbed by all 3 loads the same as the complex power being supplied by the source? It has to be. If it isn't, we're violating the laws of physics, right? So if we can calculate the complex power for load 1, the complex power for load 2, and the complex power for load 3, we can calculate this quantity S sub S, the complex power being supplied by the source, and that will inherently also give us a means by which to calculate our power factor angle. And once we know the total complex power supplied by the source, if we know the power and we know the voltage, we can back calculate to get our current. Seems reasonable enough. All right, so the complex power absorbed by load 1, let's call this SL1. I'm given apparent power, right? Which means I already know what the magnitude of my complex power is. So it's just going to be 65 kilovolt amperes with an angle of inverse cosine 0.6. So if I throw that into my calculator, I get 65 with an angle of 53.130 degrees kilovolt ampere. Nothing particularly difficult about that. For load 2, I'm not given the apparent power, I'm given the average power. So how can I get the apparent power if I know the average power and the power factor? So inherently, power factor is the ratio of the average power divided by the apparent power, right? So if I know the power factor and I know the average power, finding the apparent power should be fairly trivial, just using algebra, right? So if I divide by average power by the power factor, that has to give me my apparent power. So in this case, that would be 12 kilowatts divided by 0.98. For my angle, I will simply take the inverse cosine of my power factor. So inverse cosine of 0.98. And this is going to give me 12.245 with an angle of 11.478 kilovolt amperes. Let's see, lastly, we have the complex power absorbed by load 3. So we're going to follow a pretty similar methodology here. The apparent power is the average power, so 80. Sorry, did I say that was 80 or 30? 30. Okay, thank you. Can't read my own writing here. 30 kilowatts divided by 0.7 angle inverse cosine of 0.7. Now, one thing that we have to take into consideration here is that our power factor for load 3 is leading. So whenever we have a leading power factor, that means that we expect our angle, our power factor angle, to have a negative value. When we do the inverse cosine quantity, inverse cosine function, it will never return a negative angle. So we need to make sure that we multiply the inverse cosine function by a factor of -1 to take into account that our power factor is leading. So from this, we're going to get 30 over 0.7 with an angle of negative inverse cosine of 0.7, 42.857 with an angle of negative 45.573. Sorry, 573 degrees kVA. All right. So now we can see that the complex power absorbed, or excuse me, supplied by the source is the same as the complex powers absorbed by load 1, load 2, and load 3 combined. So if I add these numbers together, give me just a moment. I get 84.433 with an angle of 16.394 degrees kilovolt amperes. So overall, would you consider the composite load connected to our 400 volt power supply capacitive, inductive, purely resistive? How would you classify it? Positive angle, so it's an inductive load. Yeah. So the inductance of the motor is more than compensating, or the inductive reactance of the motor is more than compensating for the capacitive reactance of the railgun there. Even though the motor is actually operating at a worse power factor. All right, so from this, how can we determine our RMS current? Right? Complex power inherently is the RMS voltage, which we know, multiplied by the complex conjugate of the RMS current. So I would argue then that just using simple algebra, the RMS current is the complex power divided by the RMS voltage conjugate. Okay? I'm conjugating both the numerator and denominator of that fraction, but since the voltage has a phase angle of 0, it's not really that matter. So that is going to be 84.433 with an angle of negative 16.394 degrees kilovolt amperes. Negative angle because I'm taking the complex conjugate of that quantity. And then for my voltage, it's going to be 0.4 angle. And just to get in the habit of it, I'm saying negative 0, although it doesn't matter. Because when I take the complex conjugate of a fraction, I need to do the conjugate of both the numerator and the denominator. And this is going to be in kilovolts, so that my units should be amps RMS here. So let's store this as A. So I have the conjugate of what I have stored as A. I'm sure you guys learned it in circuits 1, but your calculator can handle all this stuff. Doesn't matter if it's in polar form, rectangular form, or whatever. It can do the conjugate operations, return real, return imaginary, give you the answers in polar form, rectangular form, blah, blah, blah. Calculators are wonderful. So be thankful you didn't have to learn how to do all of this by hand like I had to when I was way back in the day. All right, divided by 0.4 gives me 211.082 angle negative 16.394 amps. So 211 amps. That's quite a lot. Oh, and we need to determine the power factor real quick before we'll talk about this other thing, just as a quick practical application of why we're doing this. Our power factor, how are we going to get that? What now? Cosine theta s. Yeah, that's straightforward. So what's theta s here? So cosine of angle of what I have stored as A is 0.959. Leading or lagging. If I don't specify leading or lagging, I have not done enough work. It would be the same as me saying, well, there's a current of 3 amps, but not saying in which direction it flows, or a voltage of 10 volts, but not giving you the polarity. We need both the magnitude and the qualifier here. So is it leading or lagging? Pardon? Lagging because it's positive. right? Leading power factors always have a negative angle. All right, so just as a quick aside here, we know that we have a current of 211.082 amperes. So what I'm going to do is I'm going to look up an ampacity table, and let's say it's going to be in conduit, because it's very unlikely that we're just going to have live wires kind of laying around in a battleship. Seems legit. So, according to this table, as excerpted from the 2002 National Electrical Code, although to be entirely honest, these numbers probably have not changed at all in 60 plus years because the method by which they're calculated has not changed. It's called the Nair-McGrath equation that was developed in, I think, 1919, so they're sticking with that. So for a current of 212 amperes, we have multiple different wires that we can use depending on how much we allow the temperature in the insulation to rise. So what that means really is that different insulations are rated for different temperature levels, right? So if the insulation can withstand 90-degree temperatures of 90 degrees C before it starts to melt and degrade the wire, then we can use that line. If instead the insulation can only withstand 60 degrees C, then we have to use that one. So let's say that we're being on the safe side here and we're going to use a 60 degrees C insulation. That would mean that we have to use a 250 kc mil cable in order to supply power to these things. So a kc mil cable, well, I'm trying to think of the best way to put this. Let's see if we can see the dimensions. 250 kc mil dimensions. The insulated wire diameter is 0.678 inches. So this cable is almost 3/4 of an inch thick. But we technically haven't done enough here because we don't have any real safety factor built in as well, right? Typically speaking, if we want to design a cable run safely, it needs to be able to withstand 125% of its full load current. So with a full load current of 212 amps, 212 times 1.25 means we really need to be sizing for 265 amps, which means we would have to go all the way up to a 400 kc mil wire. And let's just see how big that bad boy is. If 300 kc mil is 0.73, .821 inches. So we're talking about a big fat cable to handle this. All right, so that is complex power in a nutshell, why we use it, all that kind of good jazz. It tells us effectively our specifications for designing systems. And the biggest one that we are going to be paying attention to as a practical engineer is always going to be the ampacity. Before we talk about power factor correction too terribly much, so our power factor here is actually pretty good, right? We have a power factor of 0.959 lagging. So that's actually pretty good. We're pretty close to unity. What would increasing the power factor do to the amount of current that's flowing in our system? Would it cause the current to go up or go down? the current will go down, right? So at the higher power factors we operate, the smaller conductors we can legally use or be used up to code, which means we're saving money because the less copper we use, the less money we spend. So that's really what the driving force between a lot of these NEC tables and codes and all this kind of stuff is. It's absolutely, we want to be safe, but we want to be safe in the cheapest means possible, is unfortunately how a lot of this stuff is regulated. So we will talk about power factor correction for 20 to 30 minutes on Friday, and then we'll be finished with this review section of what we did in circuits 1 and use our SETI on next Monday. We'll start talking about filters, where we're going to apply our steady state sinusoidal circuit analysis to multi-frequency circuits and kind of see what falls out and how we can design different things in that way. So unless anybody has any questions, we're going to knock off about 15 minutes early today. Anybody got anything for me? Nope. All righty. Well, I hope you guys have a good rest of your day, and I'll see you on Friday. One, two, three, four, five, six, seven, eight, and Mathern was in Zoom, so yeah, we're good.